Hello everybody. Let us start our discussion today. Remember last time we left with a crisis in physics where we said that we found this very mysterious electromagnetic wave we usually called light, and because its velocity was given in terms of properties of free space, the permittivity and permeability, people hypothesized a medium called ether. So we had the hypothesis of ether medium, where we said that light travels, speed of light is essentially 299792458 meter per second with respect to this medium called ether, or in the rest frame of ether if you wish, but let us not go into that particular type of nomenclature right now. Roughly it is 3 into 10 to the 8 meter per second. This number is, one should remember this number, it's very sacrosanct number, 299792458. But anyway, so that we say is the speed of light is this much with respect to ether. For any other reference frame, we should use the Galilean transformation to calculate its speed and proceed with that speed in case of the wave velocity of light when I write the wave equation for light. This was the understanding, or this was the hypothesis that attempted to resolve the tension in the physics, the problem or crisis in the physics. Today we'll see an experiment which tried to use this hypothesis and try to measure the velocity or the speed of the earth with respect to the ether. The idea is the following, that you have this ether medium. Assume that this ether medium is everywhere. It's literally everywhere. If you are there or not, it is, the medium is there. Okay, that is what I am trying to depict with these dots. Ether medium. And I have the earth, which we know that goes around the sun, and this is my earth, our home. It's going with a velocity v with respect to the ether medium. In the ether, light goes at c. So if the earth is going with a velocity v, fixed to the earth, if I am fixed to the earth in my reference frame, depending on the velocity of the earth with respect to the ether, I will measure the speed of light with respect to earth as either c plus v or c minus v. Speed of the earth is rather small. It's around I think 30 kilometer per second, 3000 kilometer per second. We'll come back to those numbers later. But anyway, so it is the speed of the earth, speed of the light as seen from the earth has to be calculated this way. And then Michelson and Morley in 1887, devised an experiment which then will use this fact or this hypothesis, ether hypothesis. These are the ethers everywhere, to figure out the velocity of earth or the speed of earth with respect to ether. So that was their aim, and we learn about how to do that using their experiment. Okay, now to start with, we have to learn a little bit about their apparatus. Let me write down the name of these two gentlemen because they are like they have done the most important experiment of all time, which eventually failed. They could not measure the speed of the earth with respect to ether, and that changed the entire of physics. So when you do an experiment in your lab and you don't get the result you expected, don't be afraid or ashamed. Maybe you have done the first step to change the physics again. That was not a joke. That's very important to realize that when an experiment does not give the expected result, then only you learn something out of the experiment. If it gives the expected result, well, you have expected that. So there is nothing that new that you have learned. Now, this experiment uses an apparatus which is called Michelson's interferometer. This is again a revolutionary apparatus. In 1907, Michelson got Nobel Prize for inventing this apparatus, and 110 years from then, which is not 19 but 2017, another Nobel Prize was given partly because of making the best Michelson interferometer apparatus in the world, which eventually discovered gravitational waves. So you can see 110 years apart, two Nobel Prizes on making on the same instrument. So it must be a very important and interesting instrument which works on the idea of interference. So we'll learn about the instrument a little bit. We'll not be able to, it's a very complicated instrument also, we'll not be able to learn a lot about it, but we'll just learn the piece of it which is required for our understanding of Michelson-Morley experiment. Now for this, I want to remind you of the phenomena of interference, and there is one thing which is that we need to discuss here, that the interference, we said, in this case the interference is the interference of light. And so when does the interference happens? Why does it happen? Remember, it happens because two light rays falls in somewhere where you are looking at, where you have placed the screen, maybe they're in phase or out of phase. So if they're in phase, if their phase is same, this you have learned in your +2, so I'm just borrowing your knowledge from there. In phase essentially means that they are integral multiple of 2 pi. So the phase difference, so this is the phase difference phi is integral multiple of 2 pi. So that I call in phase. I get bright fringes then. We get constructive interference which gives us bright things. On the other hand, if I have out of phase, that is odd integral multiple of pi. The phase difference is odd integral multiple of phi. That gives me dark fringes. This is the only thing that you should remember from your study of interference in your +2. And this is the only thing that you will be using anyway. Okay. So what all we have to calculate to see the use of this interferometer is how we what we all you have to calculate is what is the value of this phi, the phase difference. Okay, so let's see what is the construction of the interferometer. How does it look like? So interferometer is an object which makes interference between the light possible, and I need two sets of light rays which will either fall in phase or out of phase. So what is done is the following. So you have a light source. Okay, so the actual interferometer is more complicated. I am kind of simplifying it for you to understand it easily. How much is required for this particular course, I will only describe that much. We can discuss about it, and you can actually come and see the Michelson interferometer when you come here. If you ask me, I'll show it to you in the physics, MSc physics lab. So I have a light source. Then I have 45, something in the 45-degree angle. This something is just a glass plate. It's called a beam splitter. What it does is that it allows half of the light to pass through it. So the light which comes in here, half of the light goes there, it passes through, and the other half gets reflected. It actually happens in all glass plates. You can see there's always something gets reflected, something passes through. And then you put a mirror here. So by the time that light reaches the mirror, it gets reflected back. Let's call this, I put A here, I'll tell you what it is. It's a mirror A. This light comes back and gets reflected by this glass plate again and come this way. Okay, so that is one light path. Let's see the other light path, and let me draw it with some other color. The other part of the light goes up. I'm sorry. Okay, so I need this color. I need to remove this. Remove this. Then I come back here. Okay. It goes up, and I have another mirror over here, which I call mirror B. So it gets reflected. Now what is important for us is the part which comes through the glass plate, and it is these two beams which interferes. So imagine that the distance, so I can imagine that I have enclosed this entire thing in a L-shaped box. Okay, so I have one arm of the L like this, the other arm of the L like this, and there are holes and all, etc. And you put your eye here you put your eye to see the fringes, because that's the place where the interference happens. Okay, imagine that this length is LA and this length is LB. Okay, so now if the apparatus is kept fixed in the ether frame, means that it is not moving with respect to the ether. So let's ask the question, how much time it is taken for the white colored wiggly lines between this point goes to the mirror and come back there. So that will be this Ta, if that is the time. It's La by c while going. La is the distance it has traveled, c is the speed in the ether, and while coming back it is again La by c. If I ask you the question for the other path, you will say that okay, so that's trivial, Lb by c plus Lb by c. I can calculate the difference in time of arrival between these two light rays. So that let's do Ta minus Tb. These are just 2L A by C and 2LB by C. So this is 2 by C, La minus Lb. If I ask you, so this is time difference. If I ask you what is the phase difference between these two light rays, because that is what will give us interference. Phase difference is nothing but 2 pi divided by t. T is the time period of the light. Time period of the wave, 1 by frequency essentially. So this times Ta minus Tb, which is 2 by C La minus Lb. So that is the path difference. That is the phase difference. And if you wish, I can write the phase difference. So let's call this phi AB. I can write it in a little different way. You can quickly see that T times C is nothing but lambda. So I can also write it in terms of lambda. So this will be 2 pi by lambda two into La minus Lb. Okay, that's all right. But that's not all the interferometer is. The interferometer is a little bit more interesting. So what they did is they said that they will not keep these two mirrors exactly perpendicular to the light rays. This mirror B, they will tilt it a little bit. So they'll tilt the mirror a little bit this way or the other way. Let me put it in the other way because then explaining it will be easier. So they'll say tilt it this way. It really doesn't matter. It's just a reference, but let us say that it will tilt it this way. Now what will happen if I tilt it that way? So let me draw these two mirrors here and then I will see what will happen. So one mirror, so the tilt will be very less, but I am drawing it a little bigger here. Now what is this blue thing? This blue thing is the mirror A, but now this mirror A is, if I keep LB and LA equals to same, so let us do that. So let us say that LB equals to LA equals, let's take, so I have set up the interferometer in such a way that the two arms have the same length. So this phase difference here is essentially 0, La minus Lb is 0. but I have tilted one of the mirrors. So this mirror, as you look through here, your eye is here, as you look through here, your eye doesn't know that you have to go this way, and then there is this glass plate which reflects the light from mirror A. Your eye will see the mirror A in the kind of the blue dashed mirror over near to B. So that is what I have drawn here. So this is the reflection of mirror A, and this is the mirror B, which is tilted. Okay. And from where it is tilted, let us consider a point here, and let's say that this is Z. This distance is Z. And the angle of tilt is very small, so let's call it theta. Okay. Now you see what will happen. Because of the tilt, there is one ray which is reflecting off mirror A. So that is only reaching up to this point. But the ray which is reflecting off mirror B, that has to reach up to this point. So it has to travel an extra distance here. Actually, it has to travel twice this extra distance. If I call this distance L, extra path in the arm B, which is the vertical one now. So this will be 2 times L. 2 times because once the light is going this way, the other time it is coming back that way. So that's happening here. You remember that this is the mirror which is tilted now. Because of that tilt, it is traveling an extra path. And you see that this path is different. It depends on Z. If theta is very small, it's essentially L is Z times theta. So now when I calculate the time taken along the arm B, now TB will change. So now if I want to write TB, let me write it with white only. So remember, TA will remain same as it was before, which is essentially 2L by C. L is same in both arm now. So TB will be 2L by C plus this Z theta divided by C, right? So that's the extra path it travels. So the phase difference now, phi, is given by this only. The phase difference is 2 pi by t. Remember, that is how I convert time difference to phase difference, times tb minus ta, which is this 2z theta by c. If you wish, just like before, I can also write it as 2 pi by lambda times 2z theta. Okay, this is the phase difference, which now depends on z. So what will happen? So if I look at this edge, so I had this reflection of one mirror here and the other mirror there, and remember that this axis is z. At different values of z, my phi is now different. Phi is a function of z. Right? So now I can write this as 2 pi into 2z theta by lambda. This is my phase difference. And what do we know from our interference course? If the phase difference is multiple of 2n times pi, it is a bright fringe. If it is odd multiple of pi, it will give me destructive interference. So that portion will be dark. So now here, this is a quantity. It can be either even or odd. So for example, here I can have, so let me remove z from here so that I can put somewhere else. So z is changing this way. So this 2z theta by lambda, so this is the value of 2z theta by lambda I am writing here. This can be 0 here, it's obviously 0 there, then 1, then 2, then 3, then 4, then 5. And so these are the positions where I will see white. Here I will see white, constructive interference. Here I will see dark. Here I will see dark. Here I will see dark. So if I have to draw for you, it will look the following. So I will see white here. See again white here. Remember, I'm drawing by hand. Obviously, it may look a little bit different, but roughly this is how the interference pattern will look. This is called a pattern because you see that it's alternative white, dark, white, dark, white, dark. Okay, so this is what the Michelson interferometer gives you. And they will have constant differences between them. If I ask the question, what is the distance between two consecutive dark fringes, I leave it for you. What all you have to do is you have to set this as 2n plus 1 pi and then change n by 1. So n has a value, certain value here, and here the value of n is just one more. So if I ask this question that what is the distance between two consecutive dark fringes, I call this curly z. This you can calculate, and again I leave it to you, will be either you can write in terms of time period this way, or you can write in terms of lambda this way. This we will need later, but I leave it to you as an exercise to calculate this. It's very straightforward. So this is, we also call width of the fringe. Okay. And the width is same in everywhere in the fringe. Now this is what the Michelson's interferometer, this is the principle of working of the Michelson's interferometer. Now what we will learn is how is this used in the Michelson-Morley experiment. So that's a different question, right? This is how it is generally used. Now how it is used in the Michelson-Morley experiment. So let us start that discussion. Now really we are coming to Michelson-Morley experiment. And there is a lot to discuss here, but I will just stick to the basics. So what do they do? What they do is the following. The basic idea is this, that you have this ether which is everywhere. So that is ether. And I have earth moving through the ether. And my Michelson-Morley apparatus is obviously in the earth. So this is moving through the ether with a velocity v. Speed of light in ether with respect to ether is c. With respect to the earth, it will change using Galilean transformation. So c with respect to the earth will be c plus minus v. Okay, remember that velocity is a component. It will only change along the direction you are moving. In the other direction, it will not change. And that is the key to this experiment. Now, let me draw the Michelson-Morley apparatus like a L over here. So, and I think that you can understand what do I mean by that. So, this is the position of the mirror A, or I call this as arm A, and this I call the arm B. So, these are the position of the two mirrors. Your eye usually stays here and all, and your light source is from here. Okay, it's just a schematic drawing of the Michelson-Morley experiment. I have both of the length, the arm has length L, and this the top mirror, the B mirror is a little bit tilted. Okay, by a constant angle theta. So that theta I don't change. And this is placed on the earth. So for the first case, let us say that it is placed in such a way that this is the velocity, that's the direction of the velocity of the earth. Okay, and now we will recalculate the time taken by the light in the arm A and the time taken by the light in arm B. So let's say TA first, and let's put another suffix 1 over here, which will CY. We'll change the arrangement of the apparatus later, but let's say let's put 1 over there. Okay, so now how do I calculate this time? Well, now it is moving. Previously, remember that we were talking about in the rest frame of ether. If the apparatus is kept fixed in the ether frame. Now we have not kept it fixed in the ether frame. It's moving with a velocity v. With respect to ether along the arm A. Okay. So what will happen when the light is going this way and when the light is going this way, the effective the arc speed of the light will change. One time it will be c plus v, other time it will be c minus v. So the time taken will be L by c plus v plus, in the other case, L by c minus v. I can rearrange this. I can multiply c plus v and c minus v in the denominator. That will give me this, and I'll give you a 2c in the numerator. So this is this. And remember, the velocity of light is really much small compared to the speed of the light. Sorry, velocity of earth is much small compared to the speed of the light. So because of that, I can expand this. I can write 1 by c square minus v square. I take first 1 by c square common outside. So what I am left with is 1 by 1 minus v square by c square. And then I Taylor expand this part. So that approximately can be written as 1 plus v square by c square. Okay. So that's 2 c's in the denominator. There was 1 c in the numerator. So that cancels one of the c's in the denominator. So this becomes 1 plus v square by c square. So this is used in between these two steps. Okay. So how am I calculating this? Remember, I am calculating time. Time in terms of Galilean transformation doesn't change if I change a reference frame. So the time measured from either ether frame or the frame of the earth will be same. So that this time is calculated from a frame which is moving with velocity v with respect to ether, which is our earth frame. and this is for the journey of light in the arm A, sorry. Now for the arm B, let us calculate the time taken by light from the ether's frame. You may say that how do you calculate it in the ether's frame? The previous one you have calculated from the Earth's frame. Well, it doesn't matter. Galilean transformation tells you the time is same whether whatever frame you calculate it from. Okay. Why do I calculate it from the ether's frame? So let us see what will one person which is stationary with the ether will see about this Michelson interferometer which is moving with respect to ether. So let me first draw ether a little bit so it is all everywhere. I really wanted this color, so ether is this color. It is everywhere. So it's all ether. I am ether. Okay. So this is my apparatus. Arm A, arm B. I am talking about the motion of light in arm B, which is starting from here. It will reach that top mirror and come back. But wait a second. It takes some time for the light to go from this point to the top mirror B, which means by that time, so say the time taken is say t, so for the time being let's call it t prime. By that time the apparatus will move. How much will it move? Because it's moving with respect to ether with a velocity v, it will move a distance vt prime. So the light ray as seen from an observer in the ether will essentially look like this, and then eventually when it will come back here. It's just like the ball thrown in the train that we are talking about in the last class. As seen from a person standing on the track, we'll see the ball has a trajectory like this. Now we can calculate how much is t prime, because you see that this distance is vt prime. This distance, the vertical travel distance, is L, which is the length of the arm, and the light goes from here to there. Light has a velocity c, so it will be ct prime is that distance. Why the light has a velocity c? Well, now I am calculating in from the frame of the ether. From the frame of the ether, the light has velocity c. So you can directly use Pythagoras theorem. Ct prime square equals vt prime square plus L square. And if you calculate, this will give you t prime square as L square by square root of, square root is yet to come, L square by c square minus v square. And to the first order, again after doing all the Taylor expansions and all, this will come out to be L by c okay. you have to take c square common from here. You will get 1 minus v square by c square. And when you take square root, if you do the same type of Taylor expansion, you will get this factor of half. Now I'm not doing it strictly for you. Now this is how much time it takes to go from there to there. For the total flight, it will be twice this time. So that is 2L by C times 1 plus V square by 2C square. But that's not all. Remember that one of our mirror is a little bit tilted. One of our mirror is still a little bit tilted. And for the tilt of the mirror, the extra term we get is this 2z theta by c. So let's add that. The tilt is there in this arm. So this is 2z theta by c. And this entire thing is now TB1. So I have TA1 here. And I have TB1 here. Let us find out the phase difference, which I call phi1. The first phase difference is 2 pi by t. This we have done now several times, into TA1 minus TB1 TA1 was 2L by C into 1 plus V square by C square, and TB1 is over there, and I have that 2 minus 2z by C, 2z theta by C. Yeah, this. Fine, so one cancels out. So let me write down the let me write it down in terms of lambda maybe, or okay, so let's keep it in terms of t for the time being. So this is 2 pi by t, v square by c square, half v square by c square. So what remains is v square by c square. Sorry, what remains is L by C, v square by c square. And of course, so this is phi1, of course, minus 2z theta by c. Okay, so let us call this z1 to match with this one here. We'll see why shortly. So remember that this is when we got this. So we have this Michelson interferometer. It's on the fixed on the earth, moving with the velocity v with respect to ether. This arm is tilted. This mirror is tilted. This is my arm B. This is my arm A. The length of the L. Length, both of them are L. Okay. What will I see? Well, depending on the values of this, there is a 2 pi by t associated with this also. Depending on the values of this, I will see dark and white fringes. So I will see. So if I draw that same palette here again, so I'll see somewhere it is white, somewhere it is dark, and then again white, then again dark, etc. Okay, my drawing is not correct, so because the width of the white and dark will be similar. But that is what I see. Now what I do is, or what they did is, this is an ingenuity of this experiment. They said now we'll tilt this. So I will get the interferometer oriented this way. Now this will be this is my A arm, this is my B arm. Okay, earth velocity moving this. You just tilt it by 90 degree. Okay, what will happen? What will happen is you can now calculate, phi 2, which is for this tilt, and let me write down this for you. So you will get this. You should redo the exercise. You know exactly how to calculate, so you can redo the exercise. So you will get this if you do the exercise again. And now I write Z2, I'll say Y. Okay, so these are the two, phi 1 and phi 2, that I have. Now, what you do is, see, remember this Z1 and Z2 are essentially the position in this fringe. So Z goes this way in this plot, right? So what I do is I concentrate on a point here, which is a dark fringe. And for that, my phi 1 has a very specific value. Okay. When I come here in the tilted position, what will happen now? Because this expression is different than this expression, this entire fringe will change. And the only way it will change is that it can shift. So the fringe now will not look like the above one. Now it will look more like this. I'm sorry. Yeah, this one. Okay. So what has happened is, if I just line them up together, so the position of the dark fringes and the white fringes has changed. Well, I have not drawn it very nicely, but you can imagine that is what will happen. So now if I follow that position now has changed and come here. Okay. So obviously here, if this value is corresponds to Z1, because it has come somewhere else, this value corresponds to Z2. And that is what Z1 and Z2 in these two expression of phi 1 and phi 2. But you see, in both cases, the fringe is dark, which means the value of phi 1 here and the phi 2 here are same. I'm following the same dark fringe, which happens at different places because my expressions are different. So I can equate phi 1 and phi 2, and if I do that, I can calculate. So what do I have here? I have Z2 here and Z1 here. So I can calculate what is Z1 minus Z2. And if you do that, you will find that Z1 minus Z2 comes out to be L by theta V square by C square. So that is the change in the position of the fringe. Okay. I can also write this change in terms of the width of the fringe, which we call this Z, curly Z, the distance between two dark fringes, which we calculated sometimes earlier. Here we calculated, which is lambda by 2 theta essentially. So I can write, so this I call say delta Z. I can write delta Z by this curly Z. Curly Z is lambda by 2 theta. So if you, this will could come out to be, this comes out to be by V square by C square. Okay, so this I get. So what do I do with the apparatus? What all I do is I place the apparatus this way once with A arm along the velocity of the earth, and then this way once, B arm along the velocity of the earth, and I measure the change in the position of the fringe, black dark fringe, with respect to the width of the fringe. This I can do very well. I will know the wavelength of light used, and I have a measurement of the speed of the light. I know the length of my apparatus. I can figure out now what is the velocity of Earth. Okay. Now, velocity of Earth, as you know, you can also measure from Kepler's law, so you can see if things are consistent. Now, for Michelson-Morley experiment, the velocity of Earth, you can take around 30 kilometer per second. The length of their arms, effective length, it's more complicated, the instrument is actually more complicated, is 11 meter. Let me take it as 10 meter. They used sodium lamp, which is 6000 angstrom or 600 nanometer. Again, let me take 500 nanometer because this will make our life simple for calculations. The speed of the light, as we said, will take 3 into 10 to the 8 meter per second. So if you put these values in this expression, you will see this is supposed to be 0.4. Okay, it depends on which lambda you use and which L you use. Speed of Earth is obviously, it's a standard value, is 0.4. Okay, so if the fringe shift is about 40% of the width of the fringe, then you can measure the velocity. So that so given the velocity of the Earth is, the fringe shift was supposed to be 40% of the fringe width. What would they measure? Well, before that, precision at which they can measure this depends on some setup of the apparatus. The same number, the precision at which they could measure is 0.02. This is like if I give you a meter scale, say this scale I give you. Okay, so this scale, if you, I don't know whether you can see, but you see that these are 1 centimeter apart, and there are markings at every millimeter. So if I use this scale, I cannot obviously measure something which is less than 1 millimeter. But that was not the case for them. They could measure a relative fringe shift, the fractional fringe shift or relative fringe shift. So this is the quantity. Of the order of 0.02. And what they expect is 0.4, which is much, much larger than what they could measure. And they saw no fringe shift. So that experiment failed. It's an experiment which terribly failed. They could not measure any fringe shift. They tried a lot, but they could not measure any fringe shift. Then they came to a conclusion that then, if I cannot measure any such fringe shift, what may happen is this hypothesis, which let me measure the fringe shift, may be wrong. So you go back to square one. The crisis in the physics that we talked about last time was supposed to go away with ether hypothesis, but once the Michelson-Morley experiment happened, they could not measure any fringe shift. So the crisis remains. So that's where I will leave you today. And it's this theory of special relativity which essentially releases that crisis. And that is what we will discuss from the next class.